Let's switch gears here. I'm going to try and do some mental division, starting with dividing by my favorite number, 9. Give us a 5-digit number, and I will try and divide it by 9 in my head.
15,362.
15,362 divided by 9 should be, I get 1706.888. Okay, great. Give us a 4-digit number, please. 4321 divided by a 2-digit number. To make it a little easier, make it end in 9. 49. I'm getting 88 with a remainder of 9. That is 88 and 9/49. A little bit like 88, a little bit more than 0.18. Yeah, great. Thank you. In Lecture 6, we learned how to do math problems very quickly when they were presented on paper. We saw examples of addition, subtraction, and multiplication problems, but when it came to division, we restricted our attention to dividing numbers by 9 using the super-fast Vedic division method. In this lecture, my goal is to explore more strategies for doing division problems on paper that may be faster than anything you've seen before. What I'm especially excited to talk to you about comes from Vedic mathematics. Vedic mathematics is a collection of arithmetic and algebraic shortcut techniques, especially suitable for paper, that were popularized by a Sanskrit scholar and mathematician, Bharati Krishna Tirthaji, in the first half of the 20th century. Some of the Vedic math techniques he wrote about we've experienced already, like multiplying numbers by 11, casting out 9s, squaring numbers that end in 5, multiplying numbers near 100, and the crisscross method. In fact, most of these methods have been around for centuries, long before what is now referred to as Vedic mathematics. But the part that intrigued me the most, that I hadn't seen before, had to do with division. And as I played with it, I found that it generated answers faster than any method that I had seen before. When I've shown these techniques, teachers as well as students get very excited, and I look forward to sharing them with you in this lecture. Now, the method may seem a little strange at first. As you generate your answer, the digits of the answer actually play a role in generating more of the digits of the answer. This is kind of strange, but with just a little practice, you'll find that it's extremely efficient and rather fun to do. I should mention that I've made some modifications to the techniques and terminology. I did this to make them easier to understand and to more closely resemble modern notation. Vedic mathematics is an exciting topic, but if you get a little confused, don't panic. The process that we use here will look very different from everything else that we do in the course, and you won't need it for the other lectures, so don't worry if you don't catch everything the first time. Our focus will be on doing 2-digit division problems, but let's start by doing 1-digit division. In Lecture 4, we split a jackpot 4 ways by doing the division problem 777 divided by 4. Now, when we did the problem mentally, our process went like this. Let's see, 4 goes into 700 100 times. 777 minus 400 is 377. Now 4 goes into 377 90 times. 377 minus 360 is 17. Now 4 goes into 17 4 times with a remainder 1. And there's our answer, 194 with a remainder of 1. But when you have paper at your disposal, you can do the problem a little more quickly using the traditional method of long division. Using long division, the calculation looks like this. Long division is a little quicker than mental division because there is less demand on your memory. But when you work this problem on paper, I recommend using the process of short division, which I'll show you now. Now, many schools don't teach short division. Mine didn't, but I wish it had. We learned long division, but I never realized there was such a thing as short division. I just thought they called it long division because it took so long. With short division, you go through the same steps as long division, but there's less to write down. You do more of the math in your head, and that allows you to go faster. Let's do the last problem using short division. Okay, so what are we going to do? 4 into 7. 4 goes into 7 once with a remainder of 3. So the 1 is going to go up, and the 3 is going to go down. Okay, next, we'd have to divide 4 into 37. Now, 4 times 9 is 36. So 4 goes into 37 9 times with a remainder of 1. So the 9 goes up, and the 1 goes down. Now we have to divide 4 into 17. 4 goes into 17 4 times with a remainder of 1. That's the last digit of our problem. So the answer is 194. The 4 went up, and the remainder is 1. So there's your answer, 194 with a remainder of 1. If you compare this with long division, you see that it's much more efficient. With practice, short division is a lot faster than long division because you write down just enough to make it easier on your memory. All you ever write down is the answer with remainders along the way. Let's do one more example of short division. Let's try the problem 13571 divided by 4. Okay, so we take 4 and we divide it into 13, the first number we can. 4 goes into 13 3 times with a remainder of 1. So the 3 goes up and the 1 goes down. Next we divide 4 into what? 15. 4 goes into 15 3 times with a remainder of 3. So the 3 goes up and the remainder 3 goes down. Next we divide 4 into what? 37. 4 goes into 37 9 times with a remainder of 1. So the 9 goes up and the 1 goes down. Finally, we do 4 into 11. 4 goes into 11 twice with a remainder of 3. And there's the answer, 3392 with a remainder of 3. Notice how little we wrote down. Whereas the long division solution would have looked a lot longer like this. The short division calculation is shorter and ultimately faster. You now know everything you need to divide by one-digit numbers on paper quickly and accurately. For one-digit division, nothing beats short division, except maybe when you're dividing by 9, in which case I recommend the Vedic method that we saw earlier. For the rest of this lecture, I want to focus on dividing by two-digit numbers. Now, if you're dividing by a number between 10 and 20, then I would still recommend using short division. But if your number's 21 or larger, then I recommend using the Vedic division technique. With Vedic division, some two-digit numbers are easier to divide than others. Perhaps not surprisingly, the best two-digit numbers for Vedic division are those that end in 9. Now, why is that? You may recall in Lecture 3 that we did some 2-by-1 multiplications using the subtraction method. These problems were best suited when the two-digit number ended in a high digit, especially the number 9. So for example, we could do the multiplication problem 79 times 3 by doing 3 times 80 to get 240, then subtracting 3 to get 237. As we'll see, Vedic division is sort of like the subtraction method for division problems. So we'll start with Vedic division problems that end in 9. Our first problem will be 13571 divided by 39. Now the long division solution would look like this. If you try to do this problem by short division, you have to be very good at your multiples of 39. And you'll have quite a few three-digit subtraction problems to do in your head. That's why I would more likely do that problem by long division instead of short division. The Vedic approach makes use of the fact that it's much easier to divide by 40 instead of 39. And dividing by 40 is essentially as easy as dividing by 4. Right? For example, if when using short division, when we divided 13571 by 4, we came up with the 4-digit answer 3392.75. I call this a 4-digit answer since it has 4 digits before the decimal point. Okay, notice that if we divided 13571 by 40, what do? We simply shift the decimal point to get a 3-digit answer, namely 339.275. The Vedic strategy is to turn a hard 2-digit division problem into something that's almost as easy as a 1-digit short division problem. For example, we'll see that dividing by 39 can be made almost as easy as dividing by 4. When dividing by 39, here's what we do. We go up 1 to the nearest easy number, 40. Next we do short division, dividing by 4, but there's one shift and there's one twist. I'll explain what I mean. The shift is, since we're dividing this number by 4, that would produce a 4-digit number. But since we're really sort of dividing by 40, we want to produce a 3-digit number. So to get a 3-digit number, we simply move the remainder to the left by 1 spot. So instead of the remainder going here, it will go here instead. I refer to the number 4 as our divisor, okay? We start off as before. 4 goes into 13 3 times with a remainder of 1. So we start off just like short division. The 3 goes up and the 1 goes down. But now comes the twist. Instead of dividing 4 into 15, like we would do with short division, we divide into 15 plus 3. The 3, that little quotient digit on the top. Right? Now 15 plus 3 is 18, and 4 goes into 18 how many times? 4 times with a remainder of 2. So the 4 goes up and the 2 goes down. Now instead of dividing 4 into 27 like you would with short division, we divide it into 27 plus 4. That little quotient digit on the top. 27 plus 4 is 31. How many times does 4 go into 31? Goes into it 7 times with a remainder of 3. So the 7 goes up and the 3 goes down. When we arrive at the last digit, it's time for the remainder. And the remainder is simply 31 plus 7 to get 38. So there's our answer, 347 with the remainder of 38. And this agrees with our earlier long division calculation. I'll explain why this works shortly, but let's first get comfortable with how it works by doing another example. Let's do 79 into 2, 4, 6, 8, 10. All right? Now, as before, we add 1 to get to the nearest easy number, that's 80. Okay, so our divisor is going to be 8. Ignore the 0 there. Our divisor is 8. Now we divide 8 into the first number that we can, that's 24. 8 goes into 24 3 times with a remainder of 0. So the 3 goes up and the 0 goes down. Next we divide 8 into what number? Not the number 06, but the number 6 plus 3, 9. 8 goes into 9 once with a remainder of 1, so the 1 goes up and the 1 goes down. Okay, next, what do we divide 8 into? Not 18, but 18 plus 1, 19. Right. 8 goes into 19 twice with a remainder of 3, so the 2 goes up and the 3 goes down. Next, we divide 8 into 31 plus 2. That's 33. How many times does 8 go into 33? 4 times with a remainder of 1. So the 4 goes up, the 1 goes down. Finally, when we reach the last digit, we get the remainder, and the remainder would be 10 plus 4, which is 14. So there's the answer, 3124, with a remainder of 14. I assure you that with just a little bit of practice, this method is much quicker than doing the problem using short or long division. So why does this work? Essentially, when you divide by 79, you're dividing by 80 minus 1. So if the process subtracts off 3 multiples of 80, it needs to add back 3 to compensate, just like in the subtraction method for multiplication. If we do that last example in slow motion using long division, what you're seeing is this. 79 goes into 246. Well, you'd have to do 79 times 3 to get 237. You'd subtract 237 from 246 to get 9. Then you'd bring down the 8. The idea behind the Vedic method is that instead of dividing by 79, it's easier to divide by 80, which is essentially the same as dividing by 8. 80 goes into 246 3 times, so we subtract 240. That's an easy calculation, but we've subtracted too much. We were supposed to subtract 3 times 79, not 3 times 80, so we have to add back 3 before taking the next step. And once we do this, 6 plus 3 is 9, bring down the 8, we're at the same place we would be using long division. Here, let's do the pi problem, 3141 divided by 59. Okay, so 59, we round that up 1 to 60. So the divisor is going to be what? The divisor is going to be 6. We do 6 into 31. 6 goes into 31 5 times with a remainder of 1. So the 5 goes up and the 1 goes down. Next, we do 6 into not 14, but 14 plus 5, 19, right? 6 goes into 19 3 times with a remainder of 1. So the 3 goes up, the 1 goes down. We're at the last digit. That's our remainder. Our remainder is 11 plus 3, which is 14. So there's your answer, 53 with a remainder of 14. This is definitely shorter than long or short division. There were no multiples of 59 ever used in this problem. There's just one more situation to cover. Sometimes when you do your division step, you get a divisor that's 10 or bigger. If that happens, no problem. You just carry the tens digit into the previous column and keep going. Let me show you what I mean. Let's do 1475 divided by 29. Okay, with 29, the divisor is what? We go up 1 to 30, so the divisor is 3. 3 goes into 14 4 times with a remainder of 2, so the 4 goes up and the 2 goes down as usual. And now we do 3 into what? Not 27, but 27 plus 4, which is 31. Now 3 goes into 31 10 times with a remainder of 1. What do you do with that 10? No problem, you write down the 10, but make sure that 1 goes in the previous column for your 10. Okay, so the 10 goes up and the 1 goes down. Okay, and now we keep going. Okay, we're at the remainder step, but there is a little twist here. What's the remainder? It's not 15 plus 0, the digit in the previous column. It's 15 plus the entire 10 that you used at the last step. Okay, so 15 plus 10 is 25, and that's your remainder. And now you can read off your answer, including that little carry digit, 50, with a remainder of 25. Let's do one more example, 29 into 8876. Okay, so 29 will use a divisor of 3. 3 goes into 8 twice with a remainder of 2. So the 2 goes up and the remainder 2 goes down. Next we do 3 into 28 plus 2, which is 30. 3 goes into 30 10 times with a remainder of 0. So the 10 goes up and the 0 goes down. You see where the 10 went. Now we do 3 into what? Not into 7, not into 7 plus 0, but into 7 plus 10, 17. 3 goes into 17 how many times? 5 times with a remainder of 2. So the 5 goes up and the 2 goes down. Now we're at the last step. We're at the remainder. The remainder is not 26, but 26 plus 5, which is 31. So you could read off your answer as 305 with a remainder of 31. But notice 31 is bigger than the original divisor 29, right? So we can squeeze in an extra 29 into here. So our answer becomes 306 with a remainder of 2. The 2 was because we do 31 minus 29 to get the 2. What if the divisor does not end in 9? If the divisor ends in 8, 7, 6, or even 5, then the procedure is practically the same. Consider the problem 1, 2, 3, 4, 5, 6 divided by 78. All right, we start the problem the same as before. What's our divisor? Our divisor is 8, right? Because we went up 2 to get to 80. All right, now we divide 8 into 12. 8 goes into 12 once with a remainder of 4, so the 1 goes up and the 4 goes down. So far, nothing new. But here's the twist. If we were dividing by 79, our next step would be to divide 8 into 43 plus 1. But since we're dividing by 78, since we had to travel up 2 to reach 80, we're going to double the 1 before adding it. So instead of doing 43 plus 1, I do 43 plus 2 to get 45. That 2 is a number that I call the multiplier, and it'll be used in every step of this problem. Okay, so how many times does 8 go into 45? 5 times with a remainder of 5. So as usual, the 5 goes up, the remainder 5 goes down. Okay, next step, we do 8 into, not 50. If we were doing short division, we would do 8 into 54. If we were dividing by 79, we do 8 into 54 plus 5. But since we're dividing by 78, we do 8 into 54 plus twice 5, 54 plus 10, which is 64. And how many times does 8 go into 64? 8 times with a remainder of 0. So the 8 goes up and the 0 goes down. Next we do 8 into what? Into 5 plus 16, twice 8. Right, 5 plus 16 is 21. When I divide 21 by 8, I get 2 with a remainder of 5. So the 2 goes up and the 5 goes down. Finally, we're at the last digit for the remainder. And what will the remainder be? Not 56 plus 2, but 56 plus twice 2. 56 plus 4 to get 60. And there's the answer, 1582, with a remainder of 60. If the divisor ends in 7, you'd add 3 times the previous quotient digit. If it ends in 6, you'd add 4 times the previous quotient digit. If it ends in 5, you'd add 5 times the previous quotient digit. Let's do one more example that involves a carry. Let's try the problem 77 into 31674. Okay, so for this problem, tell me what's going to be the divisor. We're rounding 77 up 3 to 80. So the divisor is going to be 8 and the multiplier is going to be 3. Okay, so 8 goes into 31 3 times with a remainder of 7. So the 3 goes up and the 7 goes down. Now you divide 8 into what? Not 76. Not 76 plus 3, but 76 plus 3 tripled because of that plus 3 multiplier. 76 plus 9 is 85. We divide 85 by 8, no problem. That's 10 with a remainder of 5. So we put down the 10, and the 10 goes up, and the 5 goes down. All right, now we divide 8 into what? Not 57, not 57 plus 0, but not even 57 plus 10, but 57 plus triple 10, 57 plus 30, which is 87. So that means another 10 goes up, and then a 7 goes down. Finally, we're at the remainder step. The remainder is 74 plus triple 10, 104. So there's the answer. You can read it off, 410 with a remainder of 104. But since we can squeeze in an extra 77, that becomes 411 with a remainder of 27. If the divisor ends in 1, say it was 61, then you divide by 6, but then you subtract the previous quotient because you went down 1 to 60. If the divisor is 62, you're still going to divide by 6, but then you subtract twice the previous quotient, and so on. Let me show you what I mean. Let's do 61 into 2, 3, 5, 8, 13. All right, so this time we go down 1 to 60, so our divisor is 6, and our multiplier is negative 1. All right, so we begin the same as before. 6 goes into 23 3 times with a remainder of 5. Okay, and since our multiplier is negative 1, at the next step, instead of doing 6 into 55, we don't go into 55 plus 3. We're going to do 6 into 55 minus 3. That 3 and negative 1 multiply, and 55 minus 3 is 52. Okay, how many times does 6 go into 52? 8 times with a remainder of 4. Okay, so now our next step, so the 8 goes up and the 4 goes down. Now we do 6 into what? 48 minus 8. 6 goes into 40 6 times with a remainder of 4. So the 6 goes up and the 4 goes down. Next we do 6 into what? Not 41, but 41 minus 6, 35. So that 6 goes into 35 how many times? 5 times with a remainder of 5. So the 5 goes up and the remainder 5 goes down. Finally, we're at the last digit. 6 goes into 50. Well, the remainder is going to be 53 minus 5, which is 48. And there's your answer, 3865, with a remainder of 48. That may have taken a while, but it's shorter, it's faster than short or long division. If we divide by 62 instead of 61, our divisor is still 6, but now our multiplier is negative 2. That's because we had to go down 2 to reach 60. Okay, 6 goes into 23 3 times with a remainder of 5, so the 3 goes up and the 5 goes down. They always start the same way. But now the twist, 6, we divide 6 not into 55, not into 55 minus 3, but 55 minus 6 to get 49, right? You see where that 6 comes from. 3 times negative 2. Okay, 6 goes into 49 8 times with a remainder of 1, so the 8 goes up and the 1 goes down. Next we do 6 into what? Not 18, not 18 minus 8, 18 minus 16, which is 2. All right, and 6 goes into 2 0 times with a remainder of 2, so the 0 goes up, the 2 goes down. Finally, we divide, well, not finally, but we divide 6 into 21 minus 0. 6 goes into 21 3 times with a remainder of 3. Now we're at the remainder step. 6 goes in, and the remainder is going to be what? Not 33 minus 3, but 33 minus 6 to get 27. And there's the answer, 3803 with a remainder of 27. Now, in the subtraction step, you sometimes obtain negative numbers. When that happens, we have a simple adjustment. I'll illustrate this with the problem 2, 3, 5, 8, 13 divided by 64. Here, the divisor is 6, and the multiplier is -4. So we divide 6 into 23. That's 3 with a remainder of 5. So the 3 goes up, the 5 goes down. Now we do 6 into 55 minus 12. 3 times -4. 55 minus 12 is 43. 6 goes into 43 7 times with a remainder of 1. And now here comes the trouble. 6 goes into what? Then 6, we're going to divide 6 into what? Not into 18, but 18 minus 28. And that's negative 10. That's too bad, right? We can't do that. So what do we do here? When this happens, I call this an oops step, we make 2 simple adjustments. We reduce the previous quotient by 1, and we increase the remainder by the 1-digit divisor. So in this situation, we're doing 18 minus 28 is -10, and that's an oops step. So the 7 is reduced to the number 6, and the 1 is increased by the 1-digit divisor. The 1-digit divisor is 6, as in 60. 1 plus 6 is 7, and that's our new step. We have 6 as the previous quotient digit and 78 there at the bottom. Now, the reason this works is, logically, when I did 43 divided by 6 to get 7 with a remainder of 1, like we did initially, we see that runs into trouble. So instead we say, I'd rather make 43 divided by 6 equal to 6 with a remainder of 7. So my quotient's a little smaller, but I've got a bigger remainder to play with, so I'm not going to have to deal with a negative number at this step. Okay, so taking this next step, we have 78 minus 24. 78 minus 24 is 54. 6 goes into 54 9 times with a remainder of 0, but I can see already that that's going to lead into trouble, having a 9 on top and a 0 on the bottom. So instead, let's say that 54 divided by 6, instead of being 9, you're going to say it's 8 with a remainder of 6. So the 8 goes up and the 6 goes down. Now I divide 6 into 61 minus 32, which is 29. 6 goes into 29 4 times with a remainder of 5. So we're at the last. The 4 goes up, the 5 goes down. Now we're at the remainder step, which is 53 minus 16, 37. And that's the remainder. So the answer is 3684 with a remainder of 37. Naturally, to get comfortable with Vedic division, you'll need to practice. But I can speak from my own experience that with just a few hours of practice, you'll probably be able to do it faster than short or long division for most 2-digit division problems. As I mentioned before, if the divisor's between 10 and 20, I would probably stick with short division, since multiples of these numbers are easy to compute, and the Vedic method tends to produce a lot of carries or negatives. Also, if the number ends in 5, which results in the largest possible multiplier, I would instead double both numbers to simplify the problem. For example, the problem 132134 divided by 35, we can double both numbers to get 264268 divided by 70, which is much easier. There's more to Vedic mathematics than division, although we have seen much of it in this course already. Again, I would describe Vedic methods as a mixture of mental math and pencil and paper math. You're presented the problem on paper and essentially just write down the answer, but there is a lot of work that you do in your head. And as we've seen, when doing mental math, we sometimes run into serious memory limitations. In our next lecture, we'll learn a fun way to improve your ability to memorize words, lists, and especially numbers. I think you'll find it to be a memorable experience.